Okay, so I'm pleased to invite our speaker today for a seminar. He's Professor A. Gopakumar, who's from TAFR in Mumbai in India. Gopu is an expert in compact objects, gravitational waves, and he does theory work in these fields. He's also a member of LIGO and the chair of the Indian Pulsar Timing Array collaboration. And yeah, with that, you can start your
talk. Thank you. Should I just remove this from here so that
Yeah, sure.
Yes, I may not be able to see that.
Wait, is this part of this?
Yeah, I think this is here, so maybe I can. No, this I don't want. Yeah, this is better. Right? Should be good. Okay, thank you very much. I'll take care of this. Thanks. Okay, so let me introduce myself. I'm a researcher from Tata Institute of Fundamental Research. As Pawan mentioned, we are part of something called Indian Pulsar Timing Array. And we are integral part of International Pulsar Timing Array. And I'm an associate of Seoul National University. We have Center for Gravitational Wave Universe there. And Professor Himokli was actually a postdoc in CITA a long time back, who was the director of the center in Seoul. And okay, so this will be a rough outline of what I'm going to talk about. I'm going to kind of give you a promise that we may be able to do multi-band gravitational wave astronomy, and this will be kind of astronomy of a transient and persistent nature. And this should have very interesting, implication if you're looking from the astrophysical, cosmological, or theoretical physics perspective. And that's because of this international pulsar timing array efforts. And again, the point is that we hope to do what I call persistent multi-messenger nano-Hz gravitational astronomy with cosmological sources during the square kilometer array. And SK is already under construction. And so the reason why I'm going to emphasize this is that 17087, I'll come into that. What's the difference? Okay, and I presume that you know gravitational waves quite well, but I'm going to give this, kind of couple of slides, the introduction to gravitational waves. So these are essentially tidal interaction that propagate with the speed of light. So since they are tidal in nature, they are going to deform. If you consider a ring of particles, as we know in textbooks, and the gravitational waves are passing perpendicular to the screen, they kind of deform the circular ring of particle in a plus and cross manner. These are the two polarization states of gravitational waves. And so because of this deformation, it's actually easy to demonstrate that propagating gravitational waves will actually change travel time, proper time interval between these two free particles. And that's essentially how we try to look for gravitational waves these days. So laser interferometric gravitational wave observatories, they usually operate at the dark fringe, and the passing transient high significant gravitational wave events will give you fluctuating light from that dark pole. That's essentially your gravitational waves. And these transient fluctuating lights are more than enough to actually describe the astrophysical system. That's not obvious. So for example, this was the 150914. So what I show here is this 200 millisecond data. This is the time frequency map of that. So the fluctuating current light we saw at the output of those two interferometers, essentially the one in LIGO, Livingston, and in Hanford. So you can see that essentially the frequency varied from 30 to 300 hertz in 200 milliseconds. And that's all required for us to argue that this is essentially a signal from inspiral and merger of stellar mass black holes. That's very impressive, right? The reason for that is the time frequency plot, if we just do, you can actually fit f dot as a function of f following this relation, and this relation is essentially, verified by binary pulsar observations, and so immediately you get that combination of masses, and then because I said they are deforming, so their gravitational waves are sensitive to the amplitude of that gravitational wave. So I can write down that amplitude which I measured. So if I put the mass ratio to be equal, then I already measured the total mass, so I can get the distance. So in astronomy, astronomers usually ask two questions, right? What are the masses involved? How far the guys are? That's it. We got everything from here. And that's the reason this is an astronomy, right? So this is essentially merger of 30 and 35 solar mass black holes at around 400 megaparsec. We also contributed delta contribution to this. My former younger colleague, Maria Hane, constrained the orbital eccentricity, those even, and blah, blah, doesn't matter. Okay, but what's so exciting now here? Well, so let's, just like the electromagnetic window, I can look for what are the gravitational wave frequencies we can probe in the coming years. So this is the frequency as a function of the strain, the amplitude of the gravitational waves, and we are going to kind of look into binary black holes, and these are self-gravitating objects. Omega square r cube equals gm. I can rewrite that as the frequency and ask the question, what will be the peak frequency I can pick up? So that turns out to be a kilohertz times 10 solar mass divided by m. So if you put around 60, you will find gravitational waves from stellar mass binaries, black holes, to be in the LIGO frequency, hectohertz, around 100 hertz. Put a million solar mass black hole, you get it in millihertz, and if you put a billion solar mass, you get it in nanohertz. And the amplitude actually increases too. So, and you can see that this is around 10 raised to minus 22, this is around 10 raised to minus 20. We are kind of fortunate around 10 raised to minus 15, but that's a bit more complicated there. And it turned out that this is what we are trying to probe in the coming decades. And not even that, we are thinking about gravitational wave observatory in Moon. It's called Leela. It's actually by an Indian, Karan Jani, and NASA is fairly serious about this. Already $1 million, recommended. And why this is exciting? Can actually do cosmology up to kind of insane redshift of 350. This is from Karan and Avi's paper. Some of you might have seen. So this is exciting, right? So when you have this guest star of 1054, it took us almost a millennium to get this picture at various wavelengths, right? This is essentially the Kraft pulsar. You can see that it was picked up 1,000 years ago, and now you have gamma rays, you have X-rays, you have ultraviolet, infrared, whatnot. So, but this will not be the case for gravitational astronomy. So we are going to see both transient and persistent gravitational astronomy, fairly similar to what we saw during 90s, right? You have the gamma ray burst, and we also have the Kobe results, right? I mean, so, and this is the transient and persistent astronomy of the 90s, right? And so we have in very nice parallel with electromagnetic astronomies. I've said 90s when I was really young, but that's fine. The reason for all that excitement is this maturing effort of pulsar timing arrays. And I told you that we are interested in nanohertz. And so you can estimate the wavelength of those gravitational waves. That will be roughly kiloparsec. And so this is the cartoon and takeaway picture. So we have a distribution of pulsars. These are accurate clocks. And we can look for gravitational wave induced perturbation of space-time, our galaxy, created by this monster black holes out there, binaries. And that's the take-home message of this talk. By the way, please feel free to stop me. I know these are popular level, but I'm going to get a bit more detailed down the line. So what do you mean by pulsar timing array? So what we do is that we actually observe a bunch of millisecond pulsars which are within our galaxy. And of course, these are deep spectrum sources. They are fairly weak, so you need best radio telescopes over times, and that's what we do. And we can compute something called the timing residuals. I will come into that. And if those timing residuals are from individual pulsars, that's our observables. And according to general relativity, they are correlated in a quadrupolar manner. And if we can demonstrate that, we actually pick up gravitational waves from the nanohertz regime. Okay? And let me get into that, what you meant by the pulsar timing residuals. So as I told you, this is a pulsar, and I'm sure that all of you have seen and heard about it. This is the department of ULI, right? So that should be. So this is the cartoon. So this is our observable. We actually see this, burst of radio signals from pulsars, and these appear, they are millisecond pulsars. So there are thousands of pulses coming in a second. And what we do is that we take the telescope times are precious, so we actually do this in maybe 1 hour observation of some of these good millisecond pulsars, and we can actually fold. I mean, this requires us to actually detect millisecond pulsars first and then follow up. So we actually do that, and we can actually get this, the pulse shape of these pulses are very precise. So that's like our fingerprints. So we actually get that pulse shape and get the time of arrival for that epoch. And we do repeat this experiment, say after 3 weeks or something, get another time of arrival. Typically, we can connect this time of arrival to this. And so, but there will be slight differences. That's what we call residuals. So we can predict time of arrival of pulses from millisecond pulsars very precisely. How precisely? Well, for this guy, we know the rotation of that pulsar up to 18 digits in accuracy. Another way of saying is that we essentially counted something like 30 trillion rotation of this pulsar during the last 20 years so precisely. And the difference between what we can predict and what we can observe is what we call timing residual. That's the only observable we have. So this is our observation. We see pulses. These are our clocks. So in Einstein, doesn't really matter. You can measure proper distances or proper time interval. Both should give you signature of gravitational waves. And because of that ISM, we are very popular in IPTA. V means Indian Pulsar Timing Array. And I'll come to that too. Okay, so that's International Pulsar Timing Array for you. So we have the venerated Parkesville Observatory, that's in Australia, that's PPTA. Then Americans have these days GBT, that's a nanograv. And then the Europeans have a bunch of telescopes, in Germany, Italy, England. And so that's essentially is the EPTA. And Indian Pulsar Timing Array uses the upgraded giant meter wave radio telescope. And so, this is the collaboration. And these days, the mean time is also very active. So they are also kind of formally adding the data sets. So as I keep telling you, these are the Nano-Hz gravitational waves from supermassive binary black hole. So our observatory is essentially galaxy-based. So you have Earth-based, and LISA will be space-based. We already have the galaxy-based. That's essentially what we can do. Okay. And how do you know that these are interesting to you? Well, we can compute omega square r cube equal to gm, and imagine supermassive binary black hole of total mass around 10 billion. And that will give you, if the orbital separation is kind of milliparsec or 200 times the total mass of the binary, you get the orbital frequency tens of nanohertz. That's essentially what we are looking for. The amplitude, I can rewrite just the one I use for the quadrupolar formula. You can see that it's around 10 raised to minus 14, 15, depending on the year. This is actually from Steve's paper in 79. Okay, so And again, so this is the cartoon, again the take-home message, what we are trying to do here, we are essentially creating one-arm interferometer between Earth and the pulsar. And this is the binary which perturbs the space-time of the galaxy. Okay, and so it turned out that this is the scenario we are interested in. The galactic mergers should eventually lead to binary black hole formation at the galactic center via dynamical friction. That's actually related to Steve's thesis advisor. And then if there are dynamical friction later, we can actually have hydrodynamical stellar interaction to bring those binary black holes to parsec separation, and to millisecond separation, then you actually get gravitational wave emission in the nanohertz, and eventually you get a recoiling supermassive black hole after the merger. So this is the astrophysical scenario we are trying to probe, and these are essentially our, expected sources. This is the characteristic strain. I will come into that. It's essentially the amplitude of the gravitational wave. This is the frequency. So we expect there are so many binary black holes emitting nanohertz gravitational waves in our universe. We actually see a background. Another way of saying that, you look at the frequency bin of your observatory and ask how many sources are there, and I will show you that the number will be not 1, not 10, most likely billions. Okay, and that's why it's a background. And eventually we will see strong sources we should be able to resolve. That's the big exercise, and that will be this binary, which we think we will see a periodic signals. Periodic signal, if you worry only about the Earth term. And then after the merger, I told you that there's a recoil at that time, and along with the recoil, you actually get a nonlinear deformation of the space-time. That's what we call memory. Well, it's actually a hereditary contribution which is time independent. We should be able to pick that one up too. And the memory contribution can be linear or non-linear. So there are efforts to look for all that in the data sets, and some of our colleagues in NPTA work on those things too. So this is what it is. So in the timing residual, this is what we see. This is timing residual as a function of the data span we have. This is the background signal we look like. Why this is a background? Consider it's a slowly varying, it's not periodic. And if you take the FFT, the power will be peaking in the low frequency. So it's still a red noise kind of thing. This is the continuous waves I was talking about. This is the burst with memory. Essentially what happens is that the gravitational wave, changes the space-time, and it actually changes the rotation of the individual pulsars by that very tiny amount. And since we have not bothered to bring that into our timing residuals, you see this kind of a linear time in variation in timing residuals. And this is, right now it's all below our noise levels, but we hope all this will kind of start manifesting, say in 10 years time, definitely, hopefully before Lisa. Let's see. Okay. I'm going to, please feel free to stop me. I was asked whether, any time, okay? Okay, so I just want to give you a flavor of why I keep telling that this is a background, not, high significant individual transient events. So again, that game is that my frequency interval is tiny because my data span is, a decade minimum. So that's delta F is 1 over T observed. I can rewrite that dn over df times delta F. I can rewrite that again as dn over dt times df by dt inverse delta F. And this I can rewrite because these are already measured, right? There's such the time frequency map fit for me, so I can do that. And then the question is, what is dn over dt? Well, that's actually a problematic thing. So I'm going to assume for the time being there's a roughly 10 raised to 11 galaxies in our universe. And if I assume that every galaxy kind of interacts with its companion at least once in its lifetime, and I assume that that interaction will give black holes coming into milliparsec separation, then dn over dt is 10 mergers per year. This is a merger. It's kind of it may be not great, but there are better ways to do it, and I can talk about that too. So if I can do all that, you can see that the number of binary black hole in that small frequency bin around 10 nanohertz or something is going to be 10 raised to 12. You can say that my numbers are all wrong, but if I make this non-zero, this will be more than 1. And that's the background I'm talking about, okay? And so this is what we are very confident that's going to be. But there are lots of uncertainty here, right? Who told you that the galaxy mergers, which we do see, will lead to nanohertz emitting supermassive binary black hole? So if you actually measure that, then we can, try to kind of map the contribution of galaxy mergers and the dynamical friction and whatnot, everything into, our theoretical understanding. So that's what lots of astronomers and cosmologists and people like, people who used to work here are very excited about it. That kind of information is very hard to come by from other messengers. Okay, so I said a background, right? So it's a stochastic, so it's a slowly varying kind of process. So this, how do we see this? And I showed you that kind of a slowly varying timing residuals. That's what I said. It's a kind of slow drift in pulse time of arrival. This drift can be, sometimes it can be in advance or it can be a lap. But it will be a distribution, okay? And so then I can write such a distribution with an amplitude and a frequency dependent. I can show the derivation, and so I'm actually considering I'm essentially taking 2 timing residuals and finding a product of that, and I'll get into that. But since I'm talking about a stochastic process characterized by an amplitude and a frequency with an exponent, this is how it is. And it turned out that the gamma is nothing big deal, 13/3. 3 is coming from my mathematics, but -2 alpha can be argued, and alpha, when I put -2/3, which is coming from omega square r cube is gm, I get 13/3. So this is what, this is from Boris' paper a few years ago. This is from PPTA. You can see there's a constraint on the amplitude and the gamma. So this is the one we are interested, coming from the GR quadrupolar contribution. You can see that that's not exactly, this is all, there are more numbers here. If you are interested, I can explain those to you. It's because the problem is that you need to ensure that your millisecond pulsars are good clocks. So that requires noise modeling to remove all unwanted noises. So that actually changes what kind of correlation you are bringing up. Okay, so you may wonder why I should take 2 timing residuals and cross correlate. The game is that when you cross correlate 2 timing residuals, that hopefully it will enhance the signal strength and kind of bring down the noise. That's what the cross correlation should do for you. So that's what I'm taking 2 timing residuals, cross correlating them. So I get h square and alpha ij, and of course it's a function of time. And then this delta is essentially cosmic variance, because I'm not really, can also argue this because I don't have infinite time, my data set is finite, and so that's essentially this kind of fluctuation in that correlation. And I can actually compute this alpha ij in a fairly straightforward manner, and that shows that cross correlation between 2 pulsar timing residuals from 2 pulsars only going to depend on the angle subtended by those 2 pulsars on, with respect to Earth. That's this theta ij, and this is called the famous Ellingson-Down correlation. This was actually developed for something else, but is now heavily used for the PTA purposes. And unfortunately, so this was very difficult to come by. So this is again from Boris' paper. So you can see that what you do, you have many pulsars, so you actually find those correlations, and then this is a theoretical curve, which essentially this is a function of the angle, between Earth and pulsar baselines. And when because the pulsars are here, pulsars are there, pulsars here, so you make this you find various contributions. And this is essentially the box plot. It's a bit more sophisticated than that. So if the median values were on this curve, we can claim that we have actually seen in our PTA data set, the HD correlation. Unfortunately, that's not the case. So you can see that things are all over the place now. So this was the case, especially during COVID. So therefore, it was decided, a few years ago that all the PTAs will actually look at their data, kind of extend their data properly, reanalyze in a coordinated manner to clarify what we are seeing. So the reason for that is that there was a signal, there was a common red noise in pulsar timing residuals, but we could not demonstrate the HD correlation. I'm sure that maybe nanograv people might have been here last year to talk about. I'm just giving the NPTA perspective here. So the IPTA told, and then Michael is a good friend of us, so we decided EPTA and NPTA will combine our resources and then look for, what's this meaning of this correlated red noise they were seeing in the data set. So Indian pulsar timing is an Indo-Japanese effort. We initiated from NCRA and TIFR, now others have joined. And important thing is that we actually use GMRT. So, so we combine that's a big story. I'll be happy to give the details. So this is what we came up with. So again, the important thing is the correlation here. And you can see that now some of the bins are indeed falling on that curve, but not everything. So that's what we said. So this is our amplitude. This is what we expected from general relativity. Some of our data sets indeed peak in that area. So the amplitude is around 2.5 ×−15. Well, this is actually at a frequency of 1 year inverse, which we should not have done, but that's the practice. And the base factor was around 60 with respect to the common red noise. So we asked the question, do we have any evidence for a cross-correlated noise in our signal? That base factor is around 60 compared to just common current, which is common uncorrelated red noise. And the false alarm probability is around 0.1. This is the 3 sigma we were talking about. So it's not 5 sigma yet. So important point here is that we actually provided our own data, Indian data, algorithms and theoretical construct to kind of do this analysis. So that's the first time Indian data is used for gravitational wave. I just want to emphasize that a bit. So this is what, so that's the point here. When Indian pulsar timing array, we do something which is what SKA is going to do in the coming years. We can do monitor pulsars in 2 distinct frequency bands simultaneously. Because this is, we can create arrays, sub-arrays and do this. So you can see that, so simultaneous observation of 300 to 500 megahertz and L-band observations between these epochs using GMRT, and that actually allowed the noise models to get improved, and that actually goes back to kind of getting the HD correlation and better. And how good is that? I'm just going to give you a flavor of this. The plus means with Indian pulsar, Indian data, again, it's a low frequency data. So the game here is that we can control the dispersion measure much better. And dispersion measure is a chromatic noise which we want to get rid of from our data. And you can see that what happened. So the red noise which we need to quantify. So this was kind of a bimodal with EPTA data only. When we have the simultaneous data, we actually have beautiful, posterior of that red noise with that amplitude and the slope. And then this is on the DM, and of course we actually use because it's full of posteriors. We came up with a algorithm to compare posterior. That's essentially Shubhajit did that, and well, it turned out that Indians were famous for doing that. Mahanabolis and Bhattacharya and all that we just improved upon, and took help from Marco's analysis algorithm. And again, just want to emphasize this point here that for this effort, our data and algorithms were heavily used. And this also shows the importance of PTN. We are excited about it. In the current way of doing pulsar observation, we need to get the DM under control, dispersion measure, because this propagates through the interstellar medium. It's a different talk altogether. And so we need to get that dispersion measure at kind of variation in that dispersion measure, one part in something like 10,000. And in the current way, what people do is that they make the high frequency observation L band, and the low frequency will follow maybe several days later, and they don't have that kind of bandwidth of kind of 300 megahertz. So those added advantage give you all this, and we actually emphasize that point. And okay, so that's the story from the EPTA plus NPTA. But why this is exciting for lots of others? See, this is I'm talking about the timing delay. This is, as I told you, that TOAs come either ahead or behind. So that's the delay we are talking about. And you can see that this is what we expect if the binary black holes are all merging along circular orbit, but that's not what's happening. So this is the actual nanograv data. This is actually from nanograv paper. You can see that at the low frequencies, we are below the expectation, and high frequencies, what nanograv and EPTSO is above the circular supermassive binary black hole line. And this is what I just showed you. You can see that some of the low frequency things are indeed falling, but other places has gone over the way. So this created lots of excitement in other communities. So yeah, but again, I didn't tell you how do you compute this effective strain, because that was critical for all this discussion. And it's actually fairly straightforward. It's actually from Stern's paper some 25 years ago. So all I'm going to argue here is that what I'm writing here is that this is essentially energy density in gravitational wave logarithmic frequency interval. If you have actually looked at Satya and Bernice, we know why this is what it's all about, per logarithmic interval. It was confusing for me too. So I can actually write energy density in gravitational wave per logarithmic frequency interval is essentially the number density of the remnants of galactic merger or whatever times the redshifted energy each event produced in logarithmic frequency interval, dE by dFr times Fr. That's what I meant by all that. So this is what, it's just an equality. So if you want to know energy density in gravitational wave, this is what it is, right? That's all it is. And you can actually compute this expression assuming circular binaries and all that. So you can, this essentially came from the time frequency plot, essentially that same relation there. And I can plug that one in, and then I can define an effective strain F square hc square. That's this effective strain I'm talking about. And when I kind of compute this through this, you actually find hc is actually proportional to F raised to minus 2 over 3. Minus 2 over 3, we keep talking about self-gravitating binaries. That's it. It's fairly straightforward, but things get a bit more complicated because this need not be circular, this need not be even gravitational wave driven. Then the graph changes, and that's precisely what Sarah and others actually plotted in this paper. So the characteristic strain is a function of the frequency. This is the circular one we were talking about. And if you kind of put, so you can see why astronomers are excited about it. If you kind of bring in hydrodynamical effects, you can start seeing the variations is slightly different at the high frequency, especially scalar scattering and even orbital eccentricity, because now there are more harmonics, so the power get distributed. Therefore, the contribution at the lower frequencies will go down. And right now, as I was showing, right, I mean, we don't know whether that's the turnover we saw or not. So this picture tells you why not just some general relativists are interested in it. You can see that all these people are, there's a huge community there. So that's what they are. But it also shows that there's no unique way to explain what we are observing. There will be always degeneracy for the time being. It's like, 19 or 521, it's up to you which one you want to believe. So there will be lots of, and that's what, some of the nanograv and EPTA papers have at 500 plus citation, and we don't look at any of those papers, right? At least I don't even understand. So there are various ways of doing this, but these days, what does this nanograv and EPTA plus NPTA result show? Because we suspect quadrupolar correlated gravitational wave background signal in our, it looks like binary black holes are more massive and they may be more numerous to get such a strong signal than what we were expecting from typical 10 raised to 9 solar mass black holes in circular orbits. Okay. Again, why we are excited? This is from this very detailed 80-page paper from Nanograv. What I'm plotting here is this gravitational wave spectrum possible as a function of frequency. This is this bin size observation, those violin plots coming from Nanograv. So you can see that there are all sorts of possible models. There can be, this is beyond standard model. You have cosmic string. I'm not an expert on any of this. I roughly know what they are, cosmic inflation and all that. And how do you know that? Can you say that my data is consistent with more? No, because if you look at the base factor, this is all the scalar induced gravitation. You can see that the new physics plus supermassive binary black hole, they are, the base factors are comparable. They are not distinguishable for the time being, but you can't roll out new physics either. So that's the excitement. But it will take a while. But this gives this opportunity to probe many of these effects, and that's what people are excited. And interestingly, what people have not really looked at is that we actually saw a single gravitational wave event, a binary, mostly, we don't know that yet, and it's around 4.2 nanohertz with an amplitude of very strong, 14, right, 10 raised to minus 14. So we don't know this is how we see it right now, and that's why, yes.
Is there any evidence for frequency shift in that?
The turnover, is that what you mean?
No, frequency shift for that signal.
No.
If they were, okay.
Yeah, so the search is purely circular, and the pulsar terms are included. That's a frequency shift you're thinking about, it's included, it's quadrupolar. But right now, that search is only with Kern, uncorrelated red noise, and the individual binary, because the HT search is computationally a bit more complicated. We don't know how to do it, essentially. So that's the scenario for the time being. Therefore, some of the what do you call? This is one of the dark matter models which actually give continuous kind of signal, also show some signal there. So this ultra light dark matter models, which think they can affect both the clock and as well as the pulsar, kind of pick up some signal here, because that's also periodic sinusoidal signal, periodic. And
so do all the PPAs like that actually?
Both of us. The PPTA has been sort of hesitant to say anything about the background. So both EPT and NPTA, but specific data set, we see that. So why are we excited about all this? Well, people are now thinking about it. So, for example, the recent JWST, we picking up a lot of binary sort of black holes at the early universe, and many of these are dual AGNs. The fraction is around 40%. It's few percent in the local neighborhood, but that's very high. So Hamza and Abby was talking about a possible to actually explain that, so whether the dual AGNs actually light up together or something. So their argument, in order to compute the background, they argue that, well, we know from the embodied simulation merger rate of dark matter halos, and we also know scaling relation between the dark matter halos and the binary and the black hole. So we can actually connect them to And then if you do that, this is what you actually get. You can see that if assume all supermassive binary black holes are in AGN, we should have seen a very bright signal, which we are not seeing. We are seeing something. So this has interesting implication. It may be that the binary black holes are actually either merging too rapidly or not coming there at all. So we are actually looking into this and all that, and this will have lots of implication, not just for DR3 and also for LFST and others. We'll come into that if you are interested. So that's the DR3 I'm talking about. After those coordinated analysis, we are now combining our data sets with the hope that we should be able to get the phi sigma detection of the background. So this is the DR3. We will have data releases from Nanograv 15 and EPTA 20 plus, and Meerkat is also pitching in with the DR2, and the GM, we will also putting our DR2, and the FAST is not part for the time being. FAST is definitely, and there will be efforts to look for individual supermassive binary black holes, and some of our younger colleagues are very active in it. Aman is in charge of the noise analysis. This is one of the college. Shubhajit is looking into bus with memory. Abhimanyu, Loki are individual supermassive binary black hole. They are essentially in two parts of the pond. So anyway, again, so why this is sort of exciting? So I just want to emphasize that we are deeply involved in some of these efforts, and why we are exciting. So this is that the gravitational wave, energy density, which is sort of scaled with that required to close the universe. So the current things can go up to, this is around 10 raised to minus 9. That's the ratio. But with SKA, the second one on, can make a, kind of factor of million improvement, go to all the way up to 10 raised to minus 14. This is not H, I'm talking about the energy density in gravitational waves divided by what's required to close the universe. Those are dimensionless. You can see that even with the CE, we will get comparable at different frequencies. A very exciting time because of that. And at that time, of course, this will have important implication for the dark matter. I know that some of you guys are interested in that. I'll talk about, if you are interested, I'll be happy to discuss. And SK is already under construction. This is from a couple of years ago. And this is a paper from D and his student. D. Lee is in charge of FAST. So you can see that there are individual, you can see that this is the, the PPT at that time, but this was the 5-year, and when you have 10-year of SK, you can see some star dots here. Individual binary black holes will start coming up from the background. So that's sources of interest to you, OJ287. I'll jump into that in a minute. So this is D. We were kind of hanging around in Hong Kong last year. So the point here is that Nano-Hz gravitational wave emitting supermassive binary black hole individual, and will be very exciting, and SK should be able to pick up many of these. And why that's exciting? Let me go into OJ287. This is something I work on these days. So it's a blazar. It's actually in our ecliptic. You can see that it's actually very close to Gemini, the twins. And because it's an ecliptic, people were looking at it. It's order magnitude of 13 and all that. So a 50 centimeter telescope is good enough. And we have been kind of looking at multi-band electromagnetic observational campaigns, and we argue that this is most likely a binary black hole emitting Nano-Hz gravitational waves. Why is that? Well, this is the cartoon we think what's happening. This is created by, this is actually followed the Spitzer observation. So JPL created it with Abhimanyu. So we think that there is a binary black hole in that system. Let me So you can see that this is a big black hole with an accretion disk. The binary is kind of plunging through the accretion disk roughly twice in orbital period, and we can actually predict those players. Okay, that's the game. So we kind of predict those players and can have observational campaigns. the reason we need to sometimes look for the space observatory is that it's an ecliptic, comes close to the sun, then you can't use Earth-based telescopes to look at it. And fortunately for us, the Spitzer was warm, it was floating away, we could look at it and all that. So there was a prediction and all that. So this is the scenario we are kind of showing. So this is the black hole with an accretion disk, and just play that again, or I can do that here. So this is the cartoon, and we actually use general relativity. You can see that this is a precessing orbit, and whenever this passes the accretion disk, there are some astrophysical delays involved, and we can predict that flares. And if you predict the flare, you get 1 point of that orbit, so we can connect and then explain it. So that's the Spitzer we talked about. We actually wrote this proposal, so they were very amused because Spitzer was not supposed to test GR and all that, but anyway, we get some publicity. Watch it. I want to make it 1 million views, so very close to that. So these days are 15 seconds of fame. So okay, so this is the scenario we have. Many critics, they don't believe that. That's fine for us. So this is around 20 billion solar mass black hole. In a companion is around 150. It's a highly eccentric precessing orbit, and but then we can say that the problem with blazars are that they do flare. So making prediction for flares is not a big thing, but there are ways we can. But are there other ways of doing it? Well, so since it's a blazar, what's happening is that the radio jet is pointing directly at you. It's small angle, and therefore what we call the position angle of that jet, is what we measure. So you can actually see there is kind of projection. This is the jet, it gets projected onto the plane of the sky. So you actually you can base this, and that position of the jet centroid keeps moving around, okay? And in the binary black hole, we can actually model it. And we did that. So for example, this is the position angle observed at 86 gigahertz, that's a high frequency radio, as a function of time. So this is our model, and this was fitted with the early observational data. You can see that but these days, so therefore GMWave is actually kind of following this. So this is I stole from our ALMA proposal. You can see that that's what our prediction, and now we have additional points. They seem to be following. This is a GMWave paper. This will take time, but that's been done. So, and that's the reason we can talk to every once in a while. So, but the game here is that if you eventually pick up gravitational wave, if it's a binary black hole, that will be exciting, right? You're already seeing it in electromagnetic windows. That's the game we are trying to do now. And this will, of course, people criticize that, the LIGO never saw, electromagnetic observers never saw a black hole with an orbital period of, say, 10 minutes. We didn't see that, even though we see wide dwarf binaries in our galaxy with 8 minutes period. So people think that the chances of seeing that's very unlikely, but it's interesting. Now, if you have decade-long observation, so this object, PKS, is a blazar again. Roger thinks that it is indeed a binary black hole with an orbital period of something like 1700 days. So it's a GMV observation. It's just a flux density. And these days, people are now coming up with a very interesting scenario called the quasi-periodic explosions, whatever it's called. And this model is OJ2X. If you kind of look around it, they don't say that so, but interesting times. Okay, so the game is that individual supermassive binary black hole, and this is just a cartoon. Mathematics is a bit more complicated. We will need to get both the Earth and the pulsar contribution. For the background, the pulsar contributions are incoherently added, so we don't really care. But for this, we need to worry about it. And we have been spending a lot of time trying to model these things. Abhimanyu, Loki, and many others are doing this. And I've been kind of, but again, one of the bottlenecks will be accurate pulsar distances. scintillometry will be another way of doing that, and been chatting to Yuli for a while. Hopefully we can do something. And so this is the kind of prescription we develop, and it's been coordinated with this is with George and Steve and others. And in fact, Abhimanyu and Logi actually used to kind of constrain a supermassive binary black hole associate candidate in 3C66b, in the nanograv data and all that. Anyway, so again, the point here will be, if you can pick up such individual supermassive binary black hole, that will be exciting from IPTA, NGEHT, IceCube, and great observatories. That will be a very exciting time. And hopefully that can give you persistent nano-Hz gravitational astronomy. I'm done essentially. And why that's exciting? Well, this was the case. You see actually a inspiraling neutron star binary in 1708-17. This was just in the background, just in the backyard, 40 megaparsec, and the signal lasted for 100 cycles or so. And imagine a scenario, you will have such persistent gravitational waves, cosmological sources, you can do many things, right? And that's what we are trying to do. So there may be accurate measurement of the Hubble constant with or without the electromagnetic counterpart, and especially testing GR at epochs separated by thousands of years. That's not possible right now. We can do test of general relativity 50 years binary persistent. And then nonlinear and linear memory, lensing, ultralight dark matter. And again, people are now developing whatever they have done for the electromagnetic cosmological observation, CMBR kind of thing. And again, the very bright guy, Raji, and again, they are trying to kind of bring this Asian angle into all this. Okay, all this is possible thanks to Govind Swarup, who actually created Gen Beta Wave Radio Telescope. He was a professor in Stanford. There was no need for him to go back to India and work in those outskirts and create this instrument. He created GMRT for us, and he wrote in his review article in 91 that eventually GMRT should be used to detect and study a large number of millisecond pulsars to look for gravitational waves. We are just trying to do kind of tiny justice to his vision, and without him, nothing could have been possible. And when Balchandra Joshi, who some of us know here, conceptualized in PTA, this is all inspired by Govind Swarup, and this is a GMRT by him. So you can see this. These are not; they are kind of mesh. And this is like a VLA structure, and it's the middle of villages. So you can imagine radio frequency interference and all that. Lots of fun. We used to hang around, right? So, okay. So, and we can do this simultaneous multi-band millisecond pulsar observation. This is only possible with SKA right now. And we already see the strength of such observation. And actually, Balchandra has a vision. So that's in PTA. So it's a frugal collaboration. We don't have crores of rupees. We actually have zero funded compared to LIGO India. But hopefully we can do all this. That's all. And hopefully you can join us in our amazing adventure. You can see this is a very young collaboration. You can see Balchandra and few of us. It's all youngsters who are acting in here. Thank you for the privilege of your time. I will be happy to take questions.
Thank you for the talk, Sharif. You mentioned IQ. You expect specifically neutrinos coming from surface?
Oh, before that, I need to thank Yuli, and also I'm very grateful to the university. You can see that one why I'm here. That's our daughter. She's actually continuing her studies here. Maybe she can join us for dinner too. Okay, so that's it. I know people will ask me that, so I'm ready for that. So Texas source, right? So that's the blazer. We actually saw neutrinos from Texas source. And there's even a suggestion when GMVA looked at it, they suspect that this may be because of the interacting jets. And interacting jets, so now people are talking about binary black holes.
You need like a significant source of accelerated protons.
Yep, so the jet, crossing jets.
So will be jet boundaries? Because the core of the jet. will be
That's
there.
what this paper is talking about. You can see that was ice cube neutrino generated by a persisting jet-jet interaction from a binary black hole scenario possible. They did not claim it's a binary black hole because they didn't have the data or anything. But this is what the GMV observation can identify jet 1 and jet 2 when you go into 86 gigahertz resolution of the data. This paper is not part of the IceCube paper. Obviously, it came later, but it's a possibility. So people will look. There's no doubt about it. And if we can get it, amazing, isn't it? That's it.
Someone else had a question?
Yes.
Yeah, so for this question, the DM contribution for the timing residuals, do all PTA efforts use the same sort of analysis tools or consistently use the same way to take that into account?
Last sentence I missed that.
If all PTA efforts, like for instance, MUTIME or nanograph or EPK, if they all use the same way to take away the DM contribution to the timing residuals?
Yes, because we have a uniform standard for the time being, and Balchandra is kind of in PTA essentially arguing that DMX is optimal or not. So our game is that I can tell that. I mean, there may be others listening. It doesn't matter. So we have very precise 1 part in 10 raised to 4, 10 raised to 5 DM measurement as a function of time. So we are trying to do this very specialized noise analysis, individual SPNA analysis in such a way that we want to generate time series from the noise model and then compare with our DM, signal. Am I clear what I'm trying to say? Because our DM signals are, we can have both the broadband and narrowband DM. We have the methods of doing that. We want to see whether we can predict from the timing noise what we actually measure at the same time. That's the point here.
So using the timing, information together with the prediction for the DM.
Yeah, exactly, and match with the actual observation of the DM.
So you do take into account that DM will change over time.
Oh yeah, in fact, so in the case of because the observations are at different epochs, right? The low frequency observation are not simultaneous with the high frequency where we actually create the TOS. They are dominated by L-band observation. So, but you get the DM and assume that the interstellar medium is not fluctuating over days time.
Yeah, and
But there we do see differences.
in that case, if you have the DM contributions, and if you have a model for how it should behave, by any chance, have you all seen maybe anomalies on the DM contributions? It's just because we've been having talks about extreme scattering events.
Oh yeah. So some of this, so the scattering events are dominated at the low radio frequencies, L-band. So there's this huge discussion in the noise model. I'm not really that active there. So there's a paper from J. Kompa and others from IPTA talking to characterize the scattering things. And yes, so those are our worry, and it should be taken care. But right now, those are all kind of pulled behind the carpet in this. So what's the problem with that? Such chromatic noise contribution can leak into achromatic one, which is the worry we have, right? And the achromatic noise modeling, if you are not done properly, it can affect the noise, the background estimation of the gravitational wave background. So yeah, so these things will have to vary. Right now they are being done at a minimal level because again, the data spans of old data, new data, different backend, all that things have been added. So there are lots of uncertainties or parameters. All hopefully will go away, and as we can actually see in Meerkat, that's happening, right? So yeah. Are you working with Uli and others?
Not on this.
Okay. Yeah, but we should check.
Yeah, we have one more question on Zoom, and then we can carry the conversation up in the lounge. So the question is, would you be able to detect R modes from pulsars, also get pulsar spin down coefficients from the PTA?
Good question. We have the timing data. So in principle, we can use those ephemeris to argue for those. But my understanding of the armored timescales are all very short compared to the nanograv timescales. So why should I bother? I have the PTA, our pulsar timing data. Maybe we can put constraints there on the pulsar properties. So that's not really the, so I'm not so sure the time scales are different. It's like asking the, my argument will be, it will be, even if it's there, it will kind of come as a noise contribution for us, because this will be related to one pulsar most likely. Yeah, that's where I will think about. Good question, I have to think a bit more.
Yeah, would you be able to use residuals, for example, for calculating and taking account of the noise to filter out the armored gravitational wave signals?
Do you think those armored signals will be kind of 1 year, 2 year timescales?
Maybe not. They are slower.
So then they are noise essentially.
But what about LIGO and Virgo detectors? Would they be able to help in this matter?
Virgo.
LIGO and Virgo.
No. So we are. We are looking for pulsars which are very stable. So I guess for example, LIGO will be interested in things which glitch and things like that, right? And these millisecond pulsars, they don't glitch, so their profiles are very stable. So that's one way of thinking about it. Yes, there is a possibility. And again, these armodes can be excited if there's a mass transfer from the companion. And right now we are not interested in the kind of a Black Widow type system, because we have problem characterizing the deterministic timing model for them, in situ DM variations and eclipses and all that. So our pulsars are essentially uninteracting pulsar binaries. Okay, so I guess those modes excitement will be fairly difficult. I think that's the answer I can give.
Okay, thank you. Yeah.
Okay. Yeah, with that, let's thank our speaker again. Yes, so we'll continue the discussion in the upstairs lounge. Also, Gopu is going to be here throughout the week, so if you want to talk to him, please sign up on the sheet. And we have dinner today. We have a couple of spots if anyone wants to join. So again, yeah, write it on the sheet if you want to join. Thank you.